Hey guys, welcome to Unit 5.2, Solving Exponential Equations. So today we're going to talk about what happens when I have an exponential equation that cannot get down to the same base. How do we handle a situation like that? Okay, so the first thing that we have to start with is talking about two different types of logs. Okay, so there's something called common log, and that means that it has a base of 10. So these are the most real life applicable ones. They use log a lot to determine pH and things in chemistry. Anytime that you see just log with no base, they're implying that it's a 10. It's assumed that it's 10. The log button on your calculator, that's built in a base 10. Okay, and we know that 10 is like the number that the metric system is like built around. Okay, so we're going to use this common log to kind of try and help us when I have an exponential equation that doesn't get down to the same base. Okay, we'll see that in a couple minutes. All right, the other thing that we want to talk about is something called the natural log. So the natural log has a base e. E is just a number. It's irrational like pi, okay? There is an E button on your calculator. You have to do second ln, okay? And the approximation for E is 2.7183, just like pi is 3.14. All right, so instead of writing log base E is actually ln. So anytime that you have ln, that's what it really means. It means a log base E, and E is this irrational number. And we're going to use those to help us with natural base exponential equations. All right, the other thing that we want to know is that ln and E are inverses of one another. So if we were to do composition to prove inverses like we did way back when, all right, we did ln of e to the x. ln is actually log base e, so I would definitely swap that out when I was solving. And we know that when I have the same base and the same argument, that those cancel out. Okay, log base b of b equals 1. So log base e of e is going to cancel, and you're just left with x. Okay, and then kind of the same rule applies in the other direction when we do g of f of x. We do e to the ln x, okay, meaning ln x is in our exponent, okay. Base of the exponent and the base of the log are the same. Those can cancel out, and you're just left with x. So you're not responsible for this proof here that they're inverses, but I wanted to show you to try and really solidify that idea that ln and x are inverses of one another, meaning they cancel each other out, because that's going to be really instrumental in our solving. We're going to use ln and base e to cancel one another. All right, so you can see that if I have 5 to the x equals 13, there's no way for me to make any sort of factor tree to break 5 and 13 down to the same number, because we know when we have an exponential equation where they have the same base, we could cancel it out. So if I had like 3 squared equals 3 to the x, I can cancel and solve and just get x equals 2. Okay, but I can't do that if they don't have the same base. So we're actually going to use common log and base e to help us solve here. Okay, so if I'm just dealing with an exponential equation like this in example 1, so different from what's in example 2, because you can see that natural base e over there. Okay, so if it looks relatively straightforward, even though, yes, we can't make the same base, we're going to use common log. Okay, so we're actually going to take the log of both sides. So we're going to say common log of 5 to the x equals common log of 13. Okay, you want to make sure that you balance your equation. And now we're going to use the properties that we saw in 5.1 so that we can solve this. We're going to expand now. So in 5.1 we went and condensed, and now we're going to expand. So I'm going to take this x in my exponent, and I can turn, using power property, I can turn the exponent into a coefficient. So this actually becomes x times common log of 5, which equals log of 13. Well, now I can solve for x. I can get this by itself. I'm going to divide by log 5. So I have x equals log of 13 over log 5. Okay, and I can put that in my calculator. You're going to put the whole thing in. You're going to make sure that you use the fraction function. So you're going to hit green, y equals, okay, alpha y equals. You're going to bring up a fraction, and you're going to put this whole thing in at once. All right, so we're going to do log of 13 over log of 5, and we'll go over calculator commands when we're together. Okay, and we're going to round to 3 decimal places. So I get 1.5937. Okay, we're always going to make sure that we use the 4 decimal places. You want to make sure that you round appropriately. Okay, so I rounded that up to 37 because it was 369 on the calculator. All right, now example 2. I'm going to use ln to cancel out that base e. Okay, so the issue here in both of these problems is that the exponent is my variable, and that's what I'm trying to solve for. So just like when I took a common log of both sides, I'm going to take the natural log of both sides, and it actually does the same thing. So ln of e to the x equals ln of 6. If you want, on the left side, if you want to rewrite this as log base e of e to the x, I would leave it over here on the right. I'll show you why in a minute. Okay, but log base e of e to the x, that cancels. Log base e of e cancels. And you're just left with x equals ln of 6. So ln of 6 is just a number. We're going to plug that into our calculator using the ln button. It's right by the 4. So we're going to hit ln of 6, and we're going to round to 4 decimal places. I get 1.7918. Okay, and that's our approximation. So this is the basis of what we're going to do here. Okay, anytime there is a base e in the problem, we're going to use ln. And if not, we're going to use common log. To make sure that you apply these on both sides of the equation, and then we're going to use our properties. Okay, so technically over here with the ln, I just want to make a note of this. On the left side here, properties of logs do apply to natural log. So technically, you could bring that x to the front, and it could be x times ln of e. Okay, and the ln of e is still going to cancel out, and you would just be left with the x anyway. Okay, but just so that you're aware, the properties of logs do apply to natural log. All right, so now let's just look at a couple more examples of how we handle different types of problems. Okay, so I have a 4 and a 12 here. No matter what I do, I'm not going to get them down to the same base. Okay, so I'm going to take common log of both sides. And using my properties, I'm going to take 3x, which is my exponent, and I'm going to turn it into my coefficient. Okay, so I'm trying to solve for x here. In order to get everything else by itself, the 3 and the log 4, they're both multiplying by the x. So why don't I just try and divide that all out in one shot? So I can divide out by 3 log 4. Okay, and that just leaves me with x equals log 12 over 3 log 4. Okay, I'm going to plug that entire expression into my calculator. Make sure you use alpha y equals when you're trying to get a fraction. And make sure that you close the parentheses after the log. Okay, rounding to 4 decimal points, 5975. Okay, so because I could not get 4 and 12 down to the same base, I'm using common log and properties to solve. All right, so here's one that's a little bit more complicated because now the exponent is a binomial. It's x plus 2. All right, so again, common log on both sides. And I will point out that even if you can get the same base, taking the common log on both sides will always work. Okay, so I'm going to bring my exponent to the front. I'm going to use parentheses on it this time because it's a binomial. Okay, and I'm going to distribute. So I have x times log of 6 plus 2 log of 6. All right, so remember, we're trying to solve for x. So why don't I go ahead and get rid of 2 log 6 to the other side. That has no variable. It's not connected to that term. Let's just get rid of it. All right, and then to fully solve for x, I'm going to divide by log 6. Okay, we want to leave everything in terms of common log until we get to the very end and we have this one big expression. And then we're going to plug that into our calculator all together to get an approximation for. Okay, so log 18 minus 2 log 6, and then log 6 on the bottom. All right, again, just make sure that you're closing the parentheses of those logs. That's really important. Okay, we get negative 0.3869. Okay, I'm rounding to those 4 decimal points. Make sure that you're plugging these into your calculator and that you're able to get out these same values, because if you're not, then you're plugging them into the calculator wrong, and we want to make sure that we take care of that. Okay, let's keep going. All right, so now I have an exponent on both sides, okay? And not only are they on both sides, the one on the right is a binomial, okay? So this is probably the hardest type of example that you're going to encounter, all right? So we're going to take common log of both sides. Okay, and then we're going to use our properties to bring the 3x and the 5x plus 2 to the front as coefficients. And my binomial, I'm going to put in parentheses. Okay, I'm going to leave the left side just for a second, because on the right I need to distribute. I'm going to make this 5x log 4 plus 2 log 4. All right, I got to be able to separate that variable. So I have a variable in 2 places right now. I want to bring them to the same side of the equation because I got to try and somehow get the x's together. So I'm going to subtract this guy over to the left. All right, now hopefully we can see that 3x log 9 and 5x log 4, that those are not like terms. Okay, so I'm not putting them together. I needed them on the same side of the equation because I'm going to do something a little bit tricky now. I got to get my variables together. Okay, I'm trying to get the x by itself. I see that I have the x in both terms, and even though they're not like terms where I can combine them, I can take the x out as a GCF. So just on the left side, if I do GCF, I can take the x out and I get 3 log 9 minus 5 log 4. So now I've managed to get those two variables. I managed to get the two x's together. And now I kind of have them separate from those log expressions. And I can get the x totally by itself over here. Now I can divide, right? Because when you take out a GCF, you're multiplying by whatever's left in the parentheses. So that means that I can move all of that to the other side. So now I have the variable all by itself. I have x equals 2 log 4. Okay, and I can plug that whole expression into my calculator. Okay, round to 4 decimal places. So I get negative 8.1595. Okay, final answer there. So the trick step, okay, was over here where I took that variable out as a GCF. Okay, and when you have an exponent on both sides of the equation, that's what you're going to end up having to do. So you want to get those variable terms to the same side of the equation. All right, so let's take a break from common log for a second and look at base E. So these equations are actually a little bit more simple to solve. Okay, I'm going to isolate the E. I'm going to get the E by itself. So I'm going to add 12. And divide by 3. Okay, so when I take the ln here, so it's nice that ln and base E are inverses of one another and that they cancel out. Okay, unfortunately, there's no inverse for ln. I guess it would be base 10. Okay, so I'm going to take the natural log of each side. Okay, and remember, you can apply the properties here. So you could have 4x to the front and then ln of E. Okay, and I just use that cursive L so that you actually know that it's ln and it's not like a 1 or something like that. Okay, so ln of E cancels. I have 4x equals ln of 9, and then divide by 4. Okay, so x equals ln of 9 over 4. And again, that's just an expression that you can put in your calculator to evaluate. Okay, the ln button is right by the 4. So natural log of 9. Okay, we get 0.5493. Okay, still using 4 decimal places, even with base E. Okay, let's do one more base E here. Okay, so this is using a natural log now, but again, we're going to isolate the natural log. Okay, so I'm going to divide both sides by 3. Okay, 24 divided by 3, I get 8. Okay, so ln is the same thing as log base E. Okay, well, I can't take the log of both sides, or I can't take the ln of both sides if there's already an ln there. So instead, what I'm going to do is raise each side using E. So I'm going to do E to the ln of 4x, and I'm going to do E to the 8th power. Okay, we're going to use base E on each side. So rather than taking the natural log of both sides, we're going to use base E. So base E and ln over here, these are going to cancel. We have 4x equals e to the 8th. And then we're going to divide by 4. Okay, remember that e is just a number, so I can get an approximation for this in my calculator. So to raise e to a power, you're going to do second ln. That gives you the e button. Okay, so I'm looking at 745.2395. Okay, 4 decimal places. All right, so that's everything for common log, natural log, okay, and solving these exponential equations. It's really, really important that you keep your algebra nice and neat on these problems, because once you take ln of both sides, that's really the only quote-unquote pre-calc that you're doing. The rest is just algebra, trying to isolate the variable. All right, so that's everything. Make sure that your notes are complete. Write down any questions that you have. All right, we'll go over those in class, but that is it for this time. Thank you so much for watching, guys.